Welcome back. In previous classes, I was discussing about the sliding mode control for linear system as well as non-linear systems. And in sliding mode control, what is our observation? That we have two phases, particularly if I talk from the second order dynamics onward, then one phase is called the reaching phase, and once I reach the manifold, then second phase is called the sliding phase. And what is our general observation? That one can able to reach to the sliding manifold in finite time, and after that trajectory move towards the equilibrium point or towards the objective asymptotically. So now new idea comes into picture, that is called idea of terminal sliding mode control. And what is basic philosophy? Is it possible to also slide along the sliding surface in such a way such that after hitting the sliding surface I will land up to the equilibrium point in finite time. Okay. So now trajectory can actually start anywhere inside the state space, and in finite time they can reach to the equilibrium point. Okay. And somehow this is also a starting point of the higher order sliding mode control. Okay. So in this lecture I am going to cover the terminal sliding mode control, and after that what is connection between terminal sliding mode control and higher order sliding mode control. So purpose of discussion is terminal sliding mode control, and obviously we are going to cover some kind of key questions. And what is the key questions? One of the crucial property, that is called the convergence property. So how does the nonlinear sliding surface, it is possible to show that in two dimensional plane, suppose that this is x1 and this is x2, and if we are designing the linear sliding surface particularly, or some form of nonlinear sliding surface, okay, which has some kind of asymptotic kind of dynamics, it means that once s equal to 0, after that trajectory will converge to the equilibrium point asymptotically. Okay. Now we are going to look into some kind of surface, some kind of nonlinear kind of surface which will pass through the equilibrium point such that I will converge here, and in finite time I will converge to the equilibrium point. Okay. So our main goal to improve the convergence property, and due to that reason we are going to look into the question, how does the nonlinear sliding surface design achieve the finite time convergence compared to the conventional sliding mode control. What is meaning of conventional sliding mode control? That is nothing but the first order sliding mode control. So whenever we have higher order system, we are designing the sliding surface, and after that our aim to force the trajectory towards the sliding surface. Okay, and then maintain such that asymptotically I will reach. Now whenever you are going to design the nonlinear sliding surface with some kind of desired convergence property, obviously some challenge comes into picture, that is called singularity challenge. It means that it is possible to show that somewhere I need infinite gain to converge towards the equilibrium, towards the sliding surface. So how to avoid it? How to redesign the sliding surface such that one can able to resolve this problem? Okay, so that part also I am going to explore. And obviously main theme is the practical significance, because in several practical application or particularly in high precision application, we need the finite time convergence from any initial condition to the equilibrium point. Okay, and somehow terminal sliding mode control is going to address that particular problem, and due to that reason terminal sliding mode control is very, very important. So now I am going to talk about transition from linear to nonlinear sliding manifold. So what is basic philosophy of the linear sliding mode control. Suppose that I have system like x dot equal to u plus dt. For simplicity, I have taken the linear time invariant uncertain system, and this is second order system, and after that we are designing manifold like x2 plus some s or sigma, whatever you want, for in order to denote sliding variable. We are either using s or sigma, so s2 and plus c1 x1. Okay, and once s equal to 0 in finite time, then x2 equal to c1 x1. So you can see here that my closed loop dynamics, okay, once we start sliding, so that is governed by this, and this is just exponentially stable towards the equilibrium point. In several cases, you are also not able to expect the exponential stability. You are only able to expect the asymptotic stability, particularly for the nonlinear system. Okay, and obviously time of convergence is very large. Okay, because x1 tending towards 0 as t tending towards infinity. Okay, so now what is our basic philosophy? We are going to introduce some kind of non-linearity in the switching manifold. It means that now this switching manifold S is not linear combination of x1 and x2, that is some kind of non-linear combination of the x1 and x2, and basic idea is to actually accelerate the convergence when we are at the nearby of the equilibrium point. What happens? You can see this dynamics x1 dot equal to c x1. So since this is first order system, so easily I can able to plot. So this is x1, and if our initial condition is here, so you can see that x1 is positive, but x1 dot is negative. So we are going to move in this direction, but as we move closer to the equilibrium point, so rate of change is going to decrease, because rate of change is depending on x1. So if you are close to the equilibrium point, at that time rate of change is very small, and due to that reason we have asymptotic convergence. So now I have to add some kind of term which will accelerate particularly convergence in this particular region when we are closer to the equilibrium point. Okay, and using terminal sliding mode control, we can able to achieve this objective. It means that in terminal sliding mode control, equilibrium is a terminal attractor. What is meaning of terminal attractor? The term terminal referred to the equilibrium point which can be reached in finite time and stable. Okay, that is the meaning of the terminal, and due to that reason this kind of sliding mode is called terminal sliding mode control. Okay, so let us start with some kind of linear or non-linear system. Here this dynamics may be linear or non-linear. Similarly here I am assuming without loss of generality that this term b x1 and x2, that is not going to change their sign. Okay, so that is greater than 0. Okay, otherwise control design become little more complicated. I have already discussed about this. Okay, now you can see that I have designed sliding surface like this. Okay, and here I have certain kind of guidelines. So using Lyapunov theory I am going to prove that why I am assuming that p and q are positive odd integer. That is our assumption. Okay, and I am going to justify this assumption with help of the Lyapunov stability criteria. Another assumption I have, p should be greater than q. Okay, so it means that this power is going to lie between 0 to 1. Okay, now again sliding mode design I am going to do like this. When s greater than 0, then this is u plus, s less than 0, then this is u minus. I do not care about s equal to 0. Okay, because in all practical problem basically we are on the very fine vicinity of the equilibrium point. Okay, and due to that reason this kind of design is practically also giving the same performance even if I will define s equal to 0 between minus u minus to u plus. Okay, so for the theoretical point of view that representation is more elegant. Okay, but practical point of view this is okay. Okay, so what kind of modification I am going to do? I am going to do this kind of modification. So let us try to see that what basically this modification is going to introduce, such that I will able to give guarantee that once I reach to the sliding surface, then trajectory is going to converge to the equilibrium point in finite time. Okay. So now once s equal to 0, you can see here s equal to 0, then x2 is nothing but minus beta x1 q by p. Here another assumption I have, beta I am assuming that is greater than 0. Okay, so that kind of assumption I am going to maintain. Now you can see that from this dynamics x1 dot equal to x2, and due to that reason I will get this kind of dynamics during the sliding. Okay, now I have to actually solve this equation and try to see the convergence property. So since this is a scalar equation, so it is very easy to solve. What you can do, you can apply the variable separation method, and suppose that when I have heated, when trajectory is heated the sliding surface, at that time if initial condition is x1 0, and now I am assuming that due to this dynamics this will converge to the 0. Okay, so I have to perform integration between x1 0 to 0. Okay, and in this way I will get this expression. You can see here q by p, where p is greater than q, so this is going to lie between 0 to 1. So this term is always finite because x1 is finite. Okay, and denominator is also finite, and due to that reason in finite time any trajectory is going to converge from any initial condition to 0, but finite time convergence is depending on the initial condition. Initially if you hit to this surface which is actually very far from the equilibrium point, then you have to wait for more time, that is the meaning. Okay, and obviously you have parameter like beta, so you can able to accelerate it. So this idea, this basic philosophy is actually coined by this guy. This is Professor Jing Yu, and currently a professor in RMIT, and he is extensively working on this particular area. I have several collaboration with this particular professor. Now you can see that I am going to justify why I am assuming that p and q both are the odd. Okay, so in order to give justification, what I am going to do, I am going to perform the nonlinear analysis. Okay, and particularly I have to show the stability of this nonlinear system. Why this is nonlinear? Because here x1 dot equal to x1 power some kind of fractional power I have, because p is greater than q, and due to that reason I have defined the Lyapunov function like half x square. I have just one variable during the sliding phase. So v dot is x1 and x1 dot, and if you substitute the dynamics, then you will get this. Okay, now it is possible to show that this dynamics is finite time stable. Okay, before that I have to prove that v dot is negative definite. So this is negative definite only if p by q is even, and after that p greater than q. So due to this condition, same condition I have actually keep when I have defined the sliding manifold, and you can see that this is the generalization of linear manifold. Why? Because if you put p equal to q, again I will land up to the linear manifold. Okay, so what is basic idea? This term x1 power q by p is responsible for the improving the convergence towards the equilibrium point. That is the idea. So you can also able to justify this particular observation with help of the Jacobian calculation around the equilibrium point. So now I have dynamics like this x1 dot equal to beta x1 power q by p. You can calculate Jacobian about x1 equal to 0, and you can see here that what Jacobian is suggesting, since here p minus q by p this become positive, So as x1 tending towards 0, then this Jacobian is somehow related to the eigenvalue. Okay, so this is somehow idea of non-linear eigenvalue. So as x1 tending towards 0, j tending towards minus infinity. Okay, so with infinite speed I am going to hit towards the equilibrium point, and due to that reason in finite time I can able to land up. Okay, that is the basic idea. So same kind of things I have actually written, which indicate that at the equilibrium point the eigenvalue tending towards the negative infinity, and of course the system trajectory which will an infinite negative eigenvalue will converge to the equilibrium point with infinitely large speed. Okay. Now what I am going to do, one more important point before going to actually generalize this. In several previous classes I have already established that if V dot is given by this kind of differential inequality, some kind of fractional power, here alpha lie between 0 to 1, then this dynamics is finite time stable. Okay, and due to that reason I haven't included that part here. Okay, easily you can able to show this, that this is finite time stable. Okay, now what I am going to do, I am going to generalize this for any higher order single input single output system. Okay, so output variable here I am assuming that is x1. Okay, and control I have just control ut that belongs to the R. So whenever I have linear or non-linear system, so we have already seen that if I have single input single output non-linear system, so I can able to apply input output linearization, and if relative degree of the system is exactly equal to the order of the system, then system can be represented fully in chain of integrator form. Okay, similar kind of methodology is equally applicable for the linear system. Okay, so I am assuming that our system, either that is linear or non-linear, that is fully input output linearizable. Okay, it means that using output I can able to express whole system, or you can apply some kind of feedback linearization technique. You can apply feedback such that your system will convert it into chain of integrator form. Okay, so from Khalil book you can able to see that how to convert system into feedback linearizable form. Okay, where system can be represented in form of chain of integrator. What now I am going to tell you how to design terminal sliding mode control for that higher order single input single output system. Okay, so now here I am assuming that output S0 is x1. Now I am going to define x1, x0 dot means x2 and plus this term beta 1 x0 q1 by p1. So this is exactly same like the second order system. Now from here onward I have to do cascading. So now I am going to define another variable x2, and that is the differentiation of this variable. Okay, and this term again comes into picture. Similarly I can able to do this cascading up to n minus 1. Okay, and every time I am going to preserve same kind of structure, all gain beta 1 up to beta n minus 1, that should be greater than 0, pi should greater than qi. So that kind of condition I am going to maintain, and everything I am going to maintain that as a odd integer. Okay, so now what is observation? Again observation is like this. So if initial condition of the system that is far from the equilibrium point, so suppose that you can take any higher dimensional space, and suppose my equilibrium point is very very far. Okay, and if you are going to calculate this term as q by p, so since p by q by p is greater than q, so this is somehow gives us the fraction that is going to lie between 0 to 1. So magnitude of this term is very very small. Okay, and due to that reason concept of fast terminal sliding mode control comes into picture. So what is basic idea? Now you can see that this is somehow fusion of the linear as well as the terminal sliding mode control. So in order to actually increase the speed of convergence towards the equilibrium point or towards the origin. What is basic idea? You can add this linear part also. Okay. After several years, new idea of the fixed time stability concept comes into picture, and idea is actually generalization of this. So in place of x1, now you can put some kind of power that is greater than 1. Okay, and in that particular case you can able to get some more convergence. So you can see that using terminal sliding mode control, several new idea actually pop out in literature of the sliding mode control or nonlinear control theory. Okay, so if you see recent development where people are actually assuming this as they are defining a manifold like x1 dot plus alpha x1, and here they are defining some kind of term like gamma 1, and here they are taking beta and x1 and gamma 2. Okay, so now and what people are doing in order to remove the restriction that q and p is actually the odd integer, they are now redefining this as a x1 power alpha signum x1. Okay, so now there is no restriction on alpha should lie just between 0 to 1. Okay, and then we can able to proceed. Okay, so in this way people are now defining sliding surface where gamma 1 is greater than 1 and gamma 2 is going to lie between less than 1. Obviously that is lower bounded by 0. Okay, and in this way people are designing the fixed sliding mode control. And what is basic property? That now you can start anywhere in the state space, in fixed time you can able to reach here, that is independent of the initial condition. Okay, now once you define the first terminal sliding mode control, then during the sliding the trajectory is going to govern by this particular dynamics. Okay, so if you are far from the equilibrium point, your dynamics is actually approximated by this, and once you are very close to the equilibrium point, your dynamics is approximated by this. Okay, and in this way equilibrium become the terminal attractor. That is the basic idea. And obviously in this differential equation also easily you can able to calculate the time of convergence. This time of convergence calculation I have also did when I was discussing about the unit vector control. Okay, so please try to do by yourself. Okay, and since every term is finite, so we can able to show that time is also finite. Okay, now what I am going to do, I am going to improve the cascading, because I have to design hierarchical first order terminal sliding mode control. So what I am going to do, now I am going to cascade the structure. So initially in higher order sliding mode control you can see that this term was not present. Now I am going to add this term everywhere. Okay, again what I am going to do, in order to design control action, I am going to take the last dynamics, I will calculate the derivative of this, and I am going to apply the control, because whenever you are taking xn minus 1, so obviously x0 is x2, x1 dot is actually contain the information of the x2 dot, and similarly here now the last dynamics where control explicitly appear, that will appear. Okay, now you can design on off control. Okay, just k signum s you can take. Okay, and k you can keep very large. Then also you can able to show that it is possible to maintain Sn minus 1 equal to 0, and once Sn minus 1 equal to 0, then Sn minus 2 equal to 0. So next dynamics is going to collapse, and in this way I can able to progress, and finally I will reach here. Okay, so cascading kind of things are going to happen in this particular methodology. Okay, and time of convergence. So first you have to calculate the time of convergence when control will explicitly appear. So some finite time is required to collapse Sn minus 1. Similarly, Sn minus 1 to Sn minus 2, some finite time is required. But every time form of time calculation is exactly like the same. Okay, and total time of the convergence, that is given by the summation of all time of convergence. Okay, and in this way I can able to get this kind of time of convergence. So please check by doing calculation. Okay, calculation is not so difficult. Okay, each time you have to keep Sn as Sn minus 1 equal to 0, then you can calculate time. After that, Sn minus 2 equal to 0, you can calculate the time, and simply you can do the summation, because now how basically we are converging. First this dynamics will collapse, then actually next Sn minus 2 dynamics will collapse, and similarly I am going to progress, and due to that reason total time of convergence is just the linear summation of the Ti. Okay, now this philosophy looks very good. Okay, you can design the nonlinear sliding surface. Okay, and philosophy is exactly like the same. What you can do after designing sliding surface x2 plus beta x1 p by q. Okay, and then what is our aim? So let us just check at a moment. I am defining by q by p. So due to that reason here I have to define by q by p. Okay, and what I am assuming that this p should be greater than q, and p and q both are the odd. How to calculate control? In order to do calculation of control, I have to take derivative of this. So I have to calculate x2 dot, and after that here you can see that once you will calculate derivative of this, then this kind of term is going to appear. Okay, and obviously x1 dot also comes into picture. So what is difficulty with respect to this term? If you see carefully, then since denominator p is greater than q, okay, so this term, power of this is negative, so this term will appear in the negative in the denominator. So as x1 tending towards 0 and x2 equal to 0, at that time this term is going to create some kind of singularity problem. Okay, and due to that reason in literature you can able to see that several criticism comes into picture for the terminal sliding mode control. During practical implementation, it is possible to show that several times this kind of situation will not occur. Why? Because once you are in sliding phase, at that time automatically x2 equal to beta x1 power q by p, and if you substitute here, you can see that this kind of singularity kind of things is automatically compensated. Okay, it means that now singular term is actually not present, and due to that reason what happens, that if you are able to hit on the sliding surface, then your job is over, and due to that reason in several practical application you cannot able to see the singularity. Okay, so singularity is just some kind of mathematical problem, but still mathematically we have to resolve this, and due to that reason Professor Jing Yu come with another modification of the terminal sliding mode control, and that is called non-singular terminal sliding mode control. And here idea is, now in place of power on x1 you can keep the power on the x2, and here initially we are putting power on x1, that is q by p. Now on x2 we have to put power that is reverse of that, that is p by q. So you can see here that is p by q. Again, once you are in sliding phase, you can see that I can able to write beta x1 equal to x2 p by q, and p and q both are odd, so easily I can able to write x2 equal to minus beta, and obviously some power will appear here, and x1, and this whole to the power q by p. Okay, so now again x1 has some kind of power, that is fractional power, and after that I will replace x2 by x1 dot. Okay, so same kind of characteristic like singular terminal sliding mode control comes into picture. Okay, and with this modification it is possible to show now whatever problem that is encounter during the first singular terminal sliding mode control, that can be removed. Okay, and here same kind of calculation we have done. What I have done, I have taken the second order system, okay, and I have calculated x dot, and then you can see that now control is fully non-singular and property of control is exactly the same. This will go through the equilibrium point. So this is x1 and x2. So in finite time you can able to converge here, and after that in finite time you can land up to the equilibrium point. So all trajectory will end up. Now we have to show, whenever you will do modification, you have to show that in finite time trajectory will reach to the equilibrium point, and due to that reason, so for that you have to first show the reachability condition. Okay, and what is reachability condition? SS dot should be less than 0. Okay, but we have to show something more. If I want to show the finite time, so SS dot should be mod and some constant should be here. So that kind of things we have to show. Here whenever we are calculating SS dot, you can see that this term also comes into picture. Okay, so mod S is fine, constant is fine, but x2 also comes into picture. So now we have to actually check that when x1 is not equal to 0 but x2 equal to 0, so each trajectory is going to stuck on somewhere in this line or not, because once x2 is not equal to 0, okay, then everything is okay, everything is fine. In finite time I can able to converge. This will act like some kind of gain part. Okay, so I will get some kind of eta reachability condition. This is also called eta reachability condition. People are putting eta term here. So in finite time I can able to reach by Lyapunov function, you can able to show. But here during modification we get difficulty here when x1 equal to 0, and it is possible to show that even if x2 equal to 0 and x1 not equal to 0, it means that on this line trajectory never going to stay on this line. Why? You can see the dynamics. Okay, and in dynamics x2 0, if you put this equal to 0, then our dynamics is now x2 dot equal to k signum s. Okay, so I cannot able to stay here. Okay, again I will leave, and once I will hit here, okay, then our job is over. Okay, and due to that reason, now it is possible to show that when s is greater than 0, at that time x2 dot equal to minus k. Okay, and if x2 dot equal to minus k, so in finite time you can see that x2 equal to 0. Okay, and similar kind of things. It means that in finite time I can able to hit to this particular surface. Okay, and in this way Professor Jingho Yu has established this. Okay, now new era comes into picture, that is the era of higher order sliding mode control. I will formally define what is meaning of higher order sliding mode control in the next class. Okay, so now what Professor Levant has done, he was telling that singularity problem, whatever during the control calculation, what basically we are doing, suppose that I have second order system. Okay, so this system you can able to represent by sigma 1 dot equal to sigma 2, sigma 2 equal to u plus dt, something like this. Okay, now here sigma 1 is nothing but sigma and sigma 2 is sigma dot. So you can design this kind of sliding surface. Now during control calculation, okay, what basically we are doing, we are calculating s dot, that is nothing but sigma double dot, and after that we are taking the derivative of this half sigma power minus half. Okay, and after that this is sigma dot that comes into picture. Sigma dot means sigma dot, that is sigma 2. Okay, now here we are replacing u and plus dt. After that we are designing u such that we have to compensate this term. Okay, So he was telling that there is no need to compensate this term. Why? If your dynamics looks like this and if you design minus k signum s, okay, so this term will just give you the sign, okay. So this is either positive and negative, and whenever you are defining this kind of manifold, then whole plane is separated into either s greater than 0, then this side become s less than 0. What is meaning of s here? That is the non-linear combination of sigma dot and sigma power half, okay. So your differential equation is converted like this, sigma double dot minus k plus d, okay. So now if you start anywhere, okay, so in finite time you can able to reach, because now dynamics is looks like this, sigma 1 dot equal to sigma 2 equal to u plus d, where sigma 1 is sigma and sigma 2 is sigma dot, okay. So always if u is minus plus k, it is possible to show that you can able to converge here in the finite time, and due to that reason he has simply removed the singularity term, okay. And in this way he is shown that both sigma and sigma dot equal to 0 in finite time, okay. And finally they have also designed the cascaded structure for third order, fourth order or any arbitrary order, and this kind of things will satisfy some kind of a special property that is called homogeneity property, because if you scaled sigma by lambda square and sigma dot by lambda, you will get exactly same kind of sliding dynamics, okay. So this property is called homogeneity property. So based on this property he has actually defined the higher order sliding mode control. So I haven't actually talked what is meaning of higher order sliding mode control, just I am telling you that okay, you can start anywhere, and now our aim to converge here in finite time, okay. And obviously more formal definition I will discuss in the next part of this course. So terminal sliding mode control, that actually opens several avenue of fixed time stability, avenue of the higher order sliding mode control, okay. Also they are talking about how to control the time of convergence, and due to that reason terminal sliding mode has a special respect in the area of the sliding mode control, okay. So finite time convergence is guaranteed, singularity free you can able to do, and also you can able to prove the high precision application, okay. So and obviously after that higher order sliding mode control become very popular, several new things comes into picture, okay. So terminal sliding mode control delivers fast, robust performance and overcoming any traditional restrictions. So with this remark I am going to end this lecture. So thank you very much.